started this transmission media. I told you there are two types of transmissions are there. Transmission media is one is guided transmission mediums, another is unguided transmission mediums. Guided transmission medium includes two-state pair. We have seen this. We have seen two-state pair, coaxial cables, coaxial cable, and optical fiber. These are the guided transmission medium, optical fiber, right? Among these, the tremendous capacity of optical fiber is because of its carrier frequency. It is carrier frequency that is used here. It is in the 14 to 15 hertz. So it has a very high information capacity. That's why almost it has captured the whole market for high-speed LAN or the high-distance applications, right? But we'll see what are the other things. We'll see it also. And these are the guided transmission media, guided media, and also there is unguided mediums. Unguided media are also there. Open air, space, water, like these things. And the difference, keep in mind, in case of guided media, I told you last times, medium itself is the most important to determine the transmission characteristics. Right? And in case of unguided media, antenna is used, and the bandwidth of the signal transmitted by the antenna that determines the transmission characteristics. Right? So these things you keep in mind. And we have seen this when you want to analyze the performance of data communications, you have to consider two important parameters: data rate and distance. And we have seen different factors are there, like bandwidth, transmission impairments, interference, number of receivers. Those things are there, right? So we have seen comparative tables for frequency range, attenuations, and repeater spacings. Last time we have seen it. We have studied the two-state pair. Two-state pair, it's a least expensive media, right? And you see mostly it is used in the to carry the voice traffic, two-state pair. And we have seen this here actually two isolated, two insulated copper pairs. Two-state pair, two insulated copper wires arranged in a regular spiral patterns, and the number of such wires, numbers of pairs, are bundled together by wrapping them in a top sheet. There can be hundreds of pairs maybe there. And twisting length is most important. In this case, I told you twist length at the one pitch. Twist length is most important for deciding the data rate. Right. These things we have seen last times. And applications, we have seen it. It is mostly used for telephone network to carry the voice traffic using analog signalings. Of course, it supports digital signaling also. It can support analog signalings like voice signals. Also, it can support digital signaling also. Digital signaling schemes also can be used here. You see, I mean, using modem also, digital data can also be transmitted, right? And digital signaling case, in this case, data rate of the order of 10 Mbps can be achieved, right? And if you see their transmission characteristics, and also you should know about its analog signaling schemes. Amplifiers generally used for analog signaling, I told you, and digital signaling repeaters are there. Generally, it is more attenuated in case of digital signaling. Signal is more attenuated, and in this case, the repeater spacing is less, maybe 2 to 3 kilometers. Repeater spacing, and in this case, slightly higher. In this case, 5 to maybe 5 to 6 kilometer range for analog signals. And if you see the frequency characteristics, you can see this is attenuation. It is generally dB per kilometer, and frequency we just see it is in hertz. So it is 0.1 megahertz. 0.1. It is in megahertz. If you write 0.1 megahertz, better. It is okay. It will be still less. Not megahertz. Let us say it is kilohertz. 10 to the power 3. It is 10 to the power 4. It is 10 to the power 5. Here it is 1 megahertz. 10 to the power 6. Higher frequencies 10 to the power 7, like the 6. So in case of in this case, attenuation is more around 1 megahertz. It is say this thing attenuations. It is a 5, 10, 20, like these things. And then you can see it here at around 1 megahertz. Attenuation is quite high. It is quite high, right? But in coaxial cables, still several megahertz. It can extend several megahertz, right? So you see, it can be several megahertz. I mean, in case of coaxial cables, this is for two-state pair. In case of this is coaxial cables, frequency range can be extended. But in case of optical fiber, you see it is almost flat over a huge frequency range. To terahertz is almost flat frequency range is there. Attenuation is very less than around 0.2 dB per kilometers for optical fibers. So it is frequency range is very less in this case, right? In coaxial cables, yes, after 10/7, I mean slightly better. It is. You can see here. After several megahertz, it will be high. Attenuation is very high. But optical fiber almost flat response you can have it. That's why it is more attractive for long distance, for LAN, etc. And some more thing about it: these two-state pairs. You see, two-state pair is quite obvious. It is a strong function of frequency, and it is quite susceptible to interference. And because coupling of electromagnetic fields would be there. Of course, twisting can reduce by reducing the twist length, it will reduce the interference effect can be reduced. And in this case, it can be two types of two-state pair. That is, one is UTP cables, unshielded two-state pair, and another is shielded two-state pair. Unshielded two-state pair, here, I mean, the two-state pair, this can be either shielded or unshielded. Unshielded is a conventional, conventional telephonic wire. It is easy to work and easy to install. Unshielded, this is unshielded. U means unshielded. Unshielded, and it is shielded. Shielded two-state pair. It is unshielded two-state pair. Shielded. Its cost is very less in case of unshielded two-state paper, two-state pair, and but it is subject to AMI, electromagnetic interference, right? And this can be reduced if you have some shield, metallic shield around this two-state pair. Then this interference effect can be reduced. Of course, both can be used for high data rates, depending upon the twist lengths. But shielded twisted pair STP cables is more expensive and more difficult to work with. And I told last time, I told you EIA, as per EIA Electronics Industries Association, categories of UTP cables are there. Different categories are there. Cat 3, Cat 4, Cat 5, Cat 5, Cat 6. The different categories. Nowadays, Cat 6 cables are widely used. Here, more than 16 Mbps, more than 16 Mbps data rate, you can have it. Right. I mean here in this case, no, still more. Cat 3D 16 Mbps, right? And almost 100 Mbps you can have it in Cat 5, Cat 5 and Cat 6. So in this case, they can be operated more than 100 Mbps, right? Mbps data rate, Cat 5, Cat 6, right? And but it is more expensive. Cat 5, Cat 6, they are more expensive compared to Cat 3 widely used initially, and in this case, twist length is also less. It is around 0.6 to 0.85 in this range. 0.6 to 0.85 in this range. Whereas in case of Cat 3, it can be 7 to 10 centimeter. Right. The twist lengths. So twist length is most important for determining the data rates as well as the interference, for reducing the interference. So this is the twisted. This is a twisted pair. So it is least expensive, and it is generally used for supporting the voice traffic for voice telephonic lines. Right, the twisted pairs. But the telephone line it is used. Twisted pairs are the UTP or HTP cables. Next is the coaxial cables. Coaxial cables. Here you see a hollow cylindrical sheet is here. Hollow outer cylindrical conductor is here. Surround, and there will be inner conductor. A single pair conductor will be there. At the axis, along the axis. This is the outer conductor, and this is the inner conductor. So the hollow outer cylindrical conductor is there, surrounding a single inner wire conductor. Surrounding this, there will be single inner wire conductor. Surrounding this, there will be hollow outer conductor is here, and outer cylindrical conductor is here, and in between there can be dielectric materials, or there can be rings will be there. Regularly spaced insulated rings, regularly placed insulated rings can be there, insulated rings, right? Or can be dielectric materials in between, right? And everything, the whole thing is covered with a jacket or a shield, right? That is the coaxial cables. Right. And the diameter of coaxial cables, overall diameter can be 1 to 2.5 centimeters in diameter. It can be used for long distances and support more stations and shear lines. Right. And applications, if you just see, mostly it is used for television distributions, televisions distribution, can be long distance telephone transmissions, long distance telephone transmission, can be short-run computer links, can be computer system links, or can be used as a LAN. Right. Mostly it is used is a cable TV for carrying hundreds of TV channels. Cable TV is used, mostly it is used, is coaxial cables. Hundreds of TV channels can be transmitted for a few kilometers. And we have seen these, internet lines mostly at the coaxial cables. Of course, now at present, there is huge competitions for these coaxial cables with optical fibers, and of course microwave, wireless communication, microwave or satellite. And but anyway, we can use, since it is analog signaling schemes. It is analog signaling schemes here. So it is used generally for FGN scheme can be used, and here over 10,000 voice channels generally used for this. Of course, it can be used also for digital signaling, but it has better frequency characteristics than the two-state pair. Just now I have seen it, the frequency characteristics. And since it is shielded, overall jacket is easier. So you see it is susceptible to interference, and also crosstalk. Interference and crosstalk will be minimized in this case. But the constants, the principal constants in this case, attenuation, thermal noise, intermodulation noise. These are the main constants in coaxial cables. So the advantage is because of this shielded in nature, because it is shielded in nature, shield is here. So it is susceptible to interference and crosstalk. But other impairments are there, like attenuation, thermal noise, intermodulation noise. Those things are there. So this is the coaxial cables. Next, you see the optical fibers. Optical fiber. I'm giving the just brief of optical fiber communication easier. Maybe next semester you'll read in details. But optical fiber, here you see here there'll be a inner solid cylinder is here. Of course, optical fiber, it is not a conductor. It is here. It is coaxial cable, twisted pair. Those all are conductor, right? But here it is dielectric materials. It is made of glass. That is, and this inner, there will two layers are there. Actually, 3 layers are there. Just you see inner solid layer, that is called. Okay. You can see there are 3 layers are there. Inner solid cylinder made of dielectric materials, that is called core. It is called core. Am I audible? Audible? Am I audible to you? Can you unmute anyone? Am I audible? Anyone? Just I'm checking that nobody is listening. Am I audible? Can you respond? Anyone? Am I audible or not? Anyone? सब सो गया क्या? हाँ? कौन कौन है देखते हैं. Just
Yes,
discuss.
sir.
Okay. So there are inner solid layer is there, which is called core, and surrounding this core there will be another solid layer which is called cladding. Right? It's called cladding. And surrounding this cladding, these are all solid layers, but made of glass. Keep in mind, not conductors. And surrounding these claddings, this layer, there will be another layer will be there. Well, this is plastic jacket will be there. This is a jacket, right? Another layer is there which is called jacket, right? But all are important. Here actually, if you see the optical fiber working principle, here light is being probably you have read it in your 12 classes. Light is transmitted through total internal reflections. So there will be say core and there will be a clad, just two layers if you just consider. Then you see if you launch the light, light will be reflected in this way. This is simplest one, but of course there can be another concept is here. This is through ray optics, but if the fiber is of very thin, then of course this ray optics cannot be used. You have to consider the wave optics. So we'll see it. Just I'll tell you when types we'll see it, then it will be. But here you see mostly generally it is the conventional optical fibers. If it is called actually fiber, multimode fiber, which is of large core fibers, right? Fiber, multimode fibers. In this case, this ray optics can be used to explain the light energy propagations. But this is inner layer. It is called core, and outer surrounding this inner layer it is called cladding. And I have seen it is the refractive index. Obviously, it will be, so if it is N1, if it is N1's the core, and N2 if it is the refractive index N2, this is also N2, then N1 must be greater than N2, so that you can have total internal reflections. So that's what it is here. Here you see core, cladding, and surrounding this cladding, jacket will be there, because you see the dimension is of the order of micron. Just like you think about hair. So and if it is made of glass, then if you just touch it, it might break. So you need some jacket. Otherwise, it will be you see breakables. If you just touch it, I mean mechanical strength will be very, very less. So jacket must be there. Then only you can bend, you can roll it if jacket is there. Otherwise, it might break. And also, if you think about this simple core, with respect to air also, you can have total internal reflections. But you see, there can be continuum emissions, scattering will be more. So if it is, when you consider the layout, if you consider the deployment of the optical fibers, contamination will be there. So to avoid those things, this cladding layer is here, right? So that this it will increase the mechanical strength as well as the contaminations. Those things can be avoided. Surface contaminations can be avoided. So core and cladding will be there. But the concept is this: the one is of high refractive index, other is of lesser refractive index, so that light can be propagated through total internal reflections. So that is the and there are three layers: core, cladding, and jacket. Just I mentioned the importance of each layers, right? And light generally is well trapped within this core, right? That's why it is very difficult to tap a signal or tap up a signal from the core, right? And it is, since it is it is dielectric, so it is not a conductor. So you see, tapping of signal is very difficult in this case. They are high secure. They generally banking purpose, military purposes. These are very, very useful. This optical fiber. Nowadays, of course, almost maximum communication. You see, communications are based on this. I mean, the main backbone. Though wireless is here, but backbone is maybe tower to tower or the POF, called POPs, whole India if you see scenario, NK network. If POPs are there, those are interconnected through optical fibers. And after that, wireless communications, you can have it. Right. So, and if you see this optical fiber, the types can be fiber types. There can be two types. There can be step index fiber, or there can be graded index fiber. Step index fiber, there is a certain change of refractive index will be there. If it is N, this is N2, right? Certain change, step change of refractive index is there. That is step index. In GI fibers, there will be gradual refractive index will be there. Graded index means if you see there the refractive index profile. In one case, you see it is like these things. No, it is. Okay, give it this one. Simple. I'm just showing it. This is this one. This is core, and this is clad. This clad. This is the axis. Then you have seen this is N1. This is N2. That is the step index. But in case of gradient index fiber, the refractive index will be max. N1, N2 is constant, but N1 is varying. N1, this will be function of R, NR, and the maximum at the axis gradually decreases on the core clad interface. That is the GI fibers. Again, this fiber can be single mode fibers, or it can be multi-mode fibers. Single mode fiber, multi-mode fibers. Here also GI fiber can be single mode fibers, can be multi-mode fibers. In single mode fibers, only one mode will propagate. You will see it in higher semester. It is generally HE1 mode, hybrid mode. Generally, TM modes, transverse magnetic, transverse electric. They are familiar with these things. TM modes, TE modes are there in waveguide, right? But since it is solid in nature, so another class of mode will be there. That is called hybrid mode, HE11 like these things, HE01 like these things. It's a fundamental mode. It has no cutoff. So HE11 mode will propagate in SM fibers. Only one mode will propagate. But in case of MM fibers, many modes can propagate. In fact, the dimension is large. It is say 50 microns. If it is say twice A, 4 diameters. So core diameter it is around 50 microns. But in this case, twice A can be of 10 microns. You just see very, very thin in case of. That's why in this case, ray optics cannot be considered here. You have to consider the wave optics because ray optics is useful when the dimension is large. Say if you consider the camera lens, say using conventional camera, then only 1 centimeter to 2 centimeter, right? 1 centimeter, 2 centimeter, maybe more, 2.5 1 inch camera. Generally, camera what we are using camera. So in that case, you see image formation. Actually, if you see it's a lens. If you press a screen, the image will be formed by considering the ray, right? That is because the lambda wavelength of light, lambda it is you see if it is a green light, it is 0.5 microns. Where it is 0.5 micron, and here it is say 2.5 centimeters. So you just see it is 5 into 10 to the power minus 6, 0.5 into minus 6 meter in this case. You just see it. So 0.5, 0.000005, if it just it will be 4, then it is centimeter. 0.0040 is 5 centimeter will be there. So almost lambda can be treated as 0 in this case. So in that case only ray optics can be used if the dimension is large. But if it is of same dimension, say if it is 2 micron, if it is 2 micron core diameter is there, generally 2 to 10 microns, right? So if 1 micron core diameter is there, so in that case, with respect to 1, the 0.5 cannot be treated as 0. But with respect to 2.5 centimeters, you can consider 0.0005. Say these ones can be treated as 0, right? So in this case, if it is these ones. So in this way, you can see it. That's why I mentioned multi-mode fiber. The dimension is large. That time ray optics can be used, but in case of single mode fiber, only and wave optics can be used. Sometimes you have to consider the Maxwell equations, right, to explain the propagation of energy. Anyway, this details you see it. But in GI fibers, generally SM fiber is not fabricated. Only MM fiber is fabricated. That is very difficult because you have to change the refractive index within the core. So that's why it is not in practice. So GI MM fiber is used. SISM, SIMM. Or generally, but here GI fiber bandwidth is quite high, and that's why it is very useful for metro cities. GI fibers, right? But SI fibers here, SI MM fiber bandwidth is less, right? But SI SM fibers, it is used for very long distance communication. So suppose if here one continent to another continent, here to US or here to Europe, undersea cable system is there. So all cases it is SI SM fiber, single mode fiber. Bandwidth is highest in case of SI SM fibers. And SIMM fibers, very short distance communications it is used. SIMM fibers. We'll see it. You'll see in details why it is not useful for long distance communication. But dispersion effect will be too high, and in this case, dispersion will be very, very less. JMM fibers, originally metro cities, these are used because of its longer bandwidth than SIMM fibers. So, but SM fiber, one thing is this: here you have to use laser source. But MM fiber, whether it is SIMM or GIMM, non-coherent sources can be used, let's say LED, or some other sources can be used with non-coherent sources. But in this case, coherent sources can be used. And in this connections, a little bit you should know the bands. Generally, here 3 bands are there. S band, short wavelength band. S band is there. S band, it is the wavelength range. It is 1280 to 1350 nanometers, right? And C band, it is 1528 to 1560 nanometer, right? Or 1.2 microns, like this thing, 1.5 microns, like this thing. And L band, longer wavelength side is here. That is 1561 to 16, generally till this thing 20 nanometer, in this range, right? All are in the frequency of terahertz, right? So these are the different bands are used in optical fibers, and their applications, wide applications are there. It can be used LAN, MAN, WAN, local area network, LAN, local area network, metropolitan area network, wide area network. That may consist of several LANs, several MANs, wide area network. Right? Suppose if you want to cover the several buildings, within a building, LAN can be there. And metropolitan, in cities, in a city there can be metropolitan area network will be there. Different organizations, different industries can be interconnected. Right? That is MAN. And WAN is this in a city. Different in a country, different cities can be interconnected, so that can be WAN, wide area network. Right. So a very long distance communication systems, metropolitan areas, in this case can be used, and also it can support more than I mean, theoretically it has huge channel capacity, but generally it is more than 60,000 speech signals can be transmitted through optical fibers. And we consider these speech signals. Nowadays, it's a huge bandwidth available. If you consider, you'll see it, WDM systems, to some extent we'll discuss it. WDMs, DWDM system is here, wavelength division multiplexing, dense wavelength division multiplexing. Many carriers can be transmitted through the same fiber. Generally, on communication systems, it needs one carrier. For optical fiber, many such carriers can be transmitted. So 100 carriers can be transmitted. That's what called dense wavelength division multiplexing. Very similar to frequency division multiplexing, but in optical regions it is for wavelength division multiplexing. Right. Also, there can be solitary communication systems using optical fiber. Almost lipidarless communication systems are there. In details, you'll see it in the optical fiber communications, fiber optic communication subjects. Today, this much. Your time is almost completed. Next time we'll see it. Wireless communications. I'm just leaving just 1 minute. So, wireless transmission. In the wireless transmission, little bit I'll give the hints. Actually, it consists of three frequencies, three range of frequencies are there. Wireless transmissions. One is just I'm mentioning. I'll discuss next times. Microwave frequency, that is 1 to 40 gigahertz. That is the microwave frequencies. Another one is the 30 megahertz to 1 gigahertz. Gigahertz, that is the broadcast radio range. That is this microwave range. This is the radio range. And the third one is there, that is also it is the infrared range, infrared frequency range, infrared, that is 3 into 10 to the power 11 to 2 into 10 to the power 14 hertz. Just see, that is almost optical regions. Optical VIB0 is called optical regions. Above VIB0 it is called infrared range. So that is the infrared range. Little bit we'll see what kind of propagations are there. Say ground wave propagations, wireless transmission, different kinds of propagations are there. Say ground wave propagations, sky wave propagation, line of sight, those things are there. And their transmission characteristics, little bit we'll see it. Antenna factor obviously will be there in these cases, and in case of infrared, transceiver will be there. Next time we'll see it. If you have any questions, anybody quickly ask. Kamal, if you have any questions, you are only responding. Kamal, if you have any questions. Okay. Just a minute.